I am demonstrating some experiments in solid state physics laboratory. So far, I have demonstrated some transport measurement like magnetoresistance as a function of magnetic field, resistance or resistivity as a function of temperature, then Hall effect as a function of magnetic field as well as a function of temperature. Also, I have demonstrated some experiment to study the magnetic material. So, how to measure magnetic property as a function of magnetic field. So, magnetization, susceptibility, permeability, these are the parameters of magnetic material. So, for ferromagnetic material, for paramagnetic, for diamagnetic. So, these are the types of magnetic materials and how to measure their parameters like susceptibility, like magnetization, permeability. So, that we have demonstrated using VSM method, using Gauss method as well as Quine's tube method. So, there are another classes of materials that is dielectric materials. So, it is the dielectric materials and magnetic materials. There are similarities in properties of these two materials. In case of magnetic materials, whatever we tell magnetic dipole moment. In case of dielectric material, we tell this is the electric dipole moment, and dipole moments per unit volume. In case of magnetic material, we tell magnetization, and in case of dielectric material, we tell polarization. So, magnetic material basically responds to the magnetic field, and dielectric material it responds to the electric field. So, now I will demonstrate experiment how to measure dielectric constant of a dielectric material. So, measurement of dielectric constant of solids. As I describe the background of this experiment. So, there are different kind of dielectric materials like paraelectric, ferroelectric, antiferroelectric. So, it is similar to paramagnetic, ferromagnetic, antiferromagnetic. Okay. So, permittivity epsilon, that is basically in case of dielectric material. So, that is equivalent to the permeability of magnetic material. So, MH loop for ferromagnetic material or BH loop. So, that is the characteristics of ferromagnetic material. Similarly, in case of ferroelectric material, P loop is the characteristics of ferroelectric material. So, after magnetic material, we will perform some experiment on dielectric material. So, first experiment I will demonstrate how to measure the dielectric constant of a solid. So, dielectric material is an electrically insulating material, and one of the great application of this material is in capacitor. Okay. So, there are many dielectric materials, and a major portion of the dielectric materials have perovskite structure. Okay, it's a AbO3 type chemical formula of this material. So, barium titanate is a very famous ferroelectric material. So, first material if we consider in perovskite structure, so that is the barium titanate material. So, its structure, perovskite structure, this is basically cubic structure. You can see now in corner of the cubic this material A type AB3 A type atom are at the corner. So, in this case barium titanate, that is barium, and in the body center so this B type atom. So, this in this case the titanium, and at the face center they are oxygen. So, this number of atoms per unit cell is basically A type, that is 1/8 contribution from each corner. So, it will be 8 corners. So, it will be 1/8 of 8 corner. So, it will be 1, and titanium or B type, it is in body center. So, per unit cell is a 1, and face center 6 phase. So, each phase have half contribution to the unit cell. So, from 6 it will be 3. So, AbO3. So, that is the chemical formula, and this structure is called the perovskite structure, right. Now, there are other materials, famous materials, ferroelectric or dielectric material. So, dielectric metal have now some materials are ferroelectric, some materials are piezoelectric, some materials are pyroelectric. So, various kind of materials are there, and depending on their response to external parameter like electric field and some other external parameter like stress, like temperature. Okay. So, lead titanate is also called PT material, PbTiO3. So, this also ferroelectric material and having this perovskite structure, and this if this is the basic material. So, now doping with some other material like zirconium, lanthanum, zirconium. Okay. So, PZT is called lead zirconate titanate, lead lanthanum zirconate titanate, PZT material, PLZT material. So, these are also this of same kind. So, one of them we will use for this experiment, and barium titanate is basically ferroelectric material, and it has Curie temperature around 120 degree centigrade. So, below Curie temperature it is ferroelectric, and its structure is tetragonal. Means A equal to B is not equal to C. So, but other angle is 90 degree. Okay. So, its structure, if you increase the temperature, so its structure from cubic it goes to the tetragonal structure. So, that means there is a displacement along the C axis, and this this is the reason to become the ferroelectric, because ferroelectric it will have the permanent dipole moment, electric dipole moment. So, in cubic phase, generally this center of the positive charge and center of the negative charge, okay. So, it coincides, whereas in tetragonal structure what happens is there will be this center of positive charge and center of negative charge will not coincide. So, there will be distance difference in distance between these two. So, that will form basically the dipole moment. So, that is the reason of seeing this ferroelectric property. So, below this Curie temperature, not below, I think is above this Curie temperature 120 degree centigrade. So, there is a phase change from ferroelectric to paraelectric, okay, or ferroelectric to non-ferroelectric phase change at 120 degree centigrade associated with the structural phase change from tetragonal to cubic. Okay. So, this 120 degree centigrade is the Curie temperature for this ferroelectric barium titanate. Okay. So, our aim of this experiment is basically the measurement of dielectric constant as a function of temperature and find out the Curie temperature of barium titanate. So, that is the aim of this experiment. So, we have to we'll take a dielectric material, black part, this is the dielectric material, we will place between two metal plate. So, that is basically capacitor. Now, this capacitor with this dielectric material, if this separation of this metal plate is d and this dielectric material barium titanate, its a dielectric constant epsilon equal to epsilon 0 epsilon r. So, epsilon r basically is a relative dielectric constant. So, our aim is to find out this epsilon r, that epsilon 0 is dielectric constant of free space. Okay. So, this metal plate we will use, that is if their area is A and their separation is D. So, epsilon r is basically ratio of this capacitance, capacitance with dielectric and capacitance without dielectric here. Okay. So, and here is the epsilon 0 A by D here or free space. Okay. So, epsilon 0 is known, A is known, D is known. So, Ca we can calculate. So, Ca is known to us, then Cd with this dielectric, if we can measure this Cd, then we will get epsilon r. So, measuring capacitance Cd and calculating Ca from known this epsilon 0 A and D, one can find epsilon r. So, this we will find as a function of temperature, and then we will plot, and then from this plot we will find out the Curie temperature, that is around 120 degree centigrade. So, this is the theory behind this experiment. Next we will demonstrate this experiment in our laboratory. So, let us go to the experimental setup and do the experiment. So, this is the experimental setup for measuring the dielectric constant of a solid. So, here you can see this our sample, this is the sample, it is a tablet kind of things, looks like tablet. Okay. So, here you see in bottom there is a metal plate, in bottom the tablet is put on a bottom. So, I think yes. Okay. So, this is isolated from this base using the mica foil. Okay. So, for electrically isolated, only the sample have contact from bottom, this one electrode this side, okay, this one, and from top this the electrode. So, on top and bottom it is connected with these two electrode where we will apply the voltage and corresponding we will get the electric field. Now, as I told that experiment is basically will vary the temperature and measure the capacitance in presence of dielectric, okay. And then from capacitance CD we can calculate the dielectric constant epsilon r as a function of temperature. So, now this sample we have, this is the setup for applying electric field, and we have to measure the capacitance as a function of temperature. Okay. So, we need oven. So, this is basically oven, you can see it is a oven inside ceramic hole is there. Okay. So, this the oven, this outside in this inside this box, basically outside of this ceramic tube there are coils, heating coils. Okay. So, this will apply power to these coils by this, from here it is written it is a oven. Okay. So, power will apply power, and here you can see three connection, these two for applying electric field as well as for measuring the corresponding capacitance, and this blue line, this one is a temperature sensor, it is a basically thermocouple. Okay. So, it is inside this, so inside thermocouple is there. So, this through this wire will get the temperature. Okay. So, this we will put into this oven, I have to put carefully, yes, I have put inside the oven. Now, we will give power to the oven. From here I will switch on this oven, So, this is the main power and this is the power for oven. So, I switch on this power, and what is the temperature? It is showing, it is temperature is 36. So, we can set here temperature, desired temperature what you want, and is a temperature controller. Basically, if you set temperature, so it will automatically take power to reach to the set temperature. So, you can set the temperature, and for that temperature we will note down that temperature, and we have to wait for reaching that temperature, and corresponding whatever this is the capacitance meter, So, here directly it will give us it will give us the capacitance of the capacitor with this dielectric at different temperature. Okay. So, at present what is the temperature? This 41 temperature, and corresponding capacitance it is 0.46. Now, whatever the sample I showed you, it could be barium titanate, it could be lead titanate, it could be lead zirconate titanate. Okay. So, at present the sample is lead zirconate titanate, PZT material we have taken. Okay. So, we are doing experiment for, as I told, this for barium titanate we will do, but since this material, this sample is put there, that is PZT. So, we can do the experiment using this PZT. So, its Curie temperature is around 320 Kelvin, not Kelvin, 320 degree centigrade. Okay. So, that is experiment we have to do here. We can heat up to 600 degree centigrade. So, we will vary the temperature. Say here you can set the temperature at different value. So, we have set this temperature at higher temperature. So, generally one has to put at say 400 degree centigrade. So, we will do experiment starting from this 50 degree centigrade or 40 degree centigrade. Okay. It will change the temperature, it will change the temperature, this reading we will take, and corresponding what is this value that we will note down. So, temperature versus the capacitance CD that we can get from these two readings. So, it is a very simple experiment. It is compared to magnetic metal, this dielectric metal, it is easy to characterize. So, you can see this very simple setup. We need only temperature controller, okay, and one oven. This will give the variation of temperature, and we need a capacitance meter. So, capacitance meter there directly it will give the value of the capacitance, in our case this with dielectric PZT dielectric material. Okay. So, for that we are getting, you see, with temperature it is 95, now it is 0.56. So, this way just reading will change and we have to note down, and then you are getting basically, then as I told that we have to know the dimension of this material. So, here diameter is 9.97 millimeter. So, company has supplied this sample as well as this diameter, one can measure also. So, corresponding area will be this, and thickness of the sample, that is important, that is 2.45 millimeters. Okay. And epsilon 0 is this one, 8.85 into 10 to the minus 12 farad per meter. So, C0 one can calculate using this supplied data, and that is 281.9 into 10 to the minus 3 picofarad. Okay. So, C by C0, whatever C or CD I have written. So, that is this value, that is this value. So, corresponding epsilon, this basically epsilon r. So, we will get epsilon r. So, we will get epsilon r for different temperature. Then we plot it. And then if we plot it, so this type of graph, if we start from 40 degree centigrade, so this type of graph you will get. You see, it is increasing with temperature, it is increasing. Okay. So, it will increase, and it is a very huge value, this dielectric constant, it is around 20,000 this value. Okay. So, and this temperature is it's not 320, 370, 370. Oh, so it was not put properly. So, just it's adjusted itself, its position. So, here you can see this the sharp variation of this dielectric constant as a function of temperature. It is from 1500 to it is going 20,000, 1500 to 20,000. So, sensitive with temperature, and it is going, and then again after 370. So, it is a Curie temperature is not 320, it is a 370. So, 370. So, then later on it is just again decreasing. Okay. So, up to 600. So, this experiment one can do from 50 to 600 degree centigrade temperature, and we have to note down this reading and plot it and find out the Curie temperature. And this also very nice experiment to see the variation of dielectric constant from 1500 to 20,000, okay, between temperature 50 to 370. So, this is the variation of dielectric constant. So, very sensitive to the temperature. So, and it happens because basically the structure is changing, lattice parameter is changing in the metal with temperature. So, it is a very structure sensitive, and this lattice parameter sensitive. So, that is why this so sharp change is observed with temperature. So, I think one has to continue taking this reading. You can see that it is increasing, so up to 370 it will increase, then it will start to decrease. So, one has to note down. So, very simple experiment, very simple experimental setup, but it can give very sensitive information that dielectric constant is a function of temperature, and in this sample it is the like magnetic metal, ferromagnetic to paramagnetic phase transition one can see. So, here ferroelectric to paraelectric phase transition one can observe from this simple experiment. So, this is the dielectric material. In dielectric, this is the ferroelectric material. Okay. It has another very good application. This is the basically is the piezoelectric material. With pressure also, this material with pressure, with stress, this material also very sensitive. This its polarization is very sensitive. So, people use this material as a piezoelectric material also. So, now it is 204 and this value is it is 0.9. So, it's reading something is happened. I think one has to check. So, I should not put my hand because this some voltage is there. Oh, I think one should change range or something can be done. Okay. Oh, some connection, I think some loose connection one has to check because things are getting heated and okay. Okay. So, some connection contact issue was there. So, one has to check and do the experiment. So, I think I will stop here. One has to continue the experiment and take the reading. Okay. So, Let us stop here. Thank you.